So welcome everybody to our latest DBio webinar workshop event. We're trying to do approximately monthly an online event for members of the DBio community and others who may not be members but find the topic interesting. So I'm Nancy Ford. I'm a professor of physics at Simon Fraser University, and I'm an executive member of the DBio. I'm a member at large of the DBio executive, and I'm also chair of our community outreach and engagement committee who's been putting these on. So I'd like to just quickly show you how to learn more about these events. If you heard about this through colleagues or other things and are interested in others. So if you go to our DBio homepage, there's a number of links. If you're not a DBio member, you could join DBio and we would love that. But if you click on workshops and networking, then you can see some of the past events that we have hosted in this year, and also some upcoming events. So we did have a meeting in August about teaching biological physics, and I think that spawned this current event because there was a lot of interest in continuing discussions around this. So here we are in November. We have an upcoming event about the future of biological physics that's happening pretty soon, a week and a half from now, and it'll be talking about research and training. So you may be interested in joining us for that. There's an upcoming session that's set for training as postdocs. So if you know of people interested in that or you are interested in that, please join us. And any of the past events that we have hosted have been recorded, just like today's event is being recorded. So if you want to catch up on something you've missed, you can go here and watch the video of the event. So we're always open to suggestions of new things to do. And it seems like this series is working pretty well. So I think we'll probably continue it next year past the March meeting. So yeah, please reach out if you have suggestions of things that we could do to help serve our community and bring people together online. And with that, I'm going to turn it over to Catherine Crouch, who's volunteered to organize this panel for us.
Great, thank you, Nancy. Just wanted to give you a quick introduction to what's going to happen today. And the main feature is hearing from our three panelists and then having the chance to discuss what they share and both share your own experiences related to it and ask follow-up questions. So when we were designing this panel, which as Nancy mentioned, grew out of this interest, this general interest in how can physics of living systems be more a part of undergraduate education. Several of us who had begun a conversation about this earlier identified basically 4 overlapping, non-exclusive, what you might call lanes or ways of incorporating this into undergraduate programs. And the first might be, my animation is responding slowly. What is happening here? I'm so sorry. I'm having Zoom issues here. All right, well, I will just tell you what the 4 lanes are without using a slide. The first is kind of incorporate physics of living systems anywhere that it comes up naturally in the curriculum. Throw in examples in all of the courses that we already have. A second, what you might call kind of doubling down on special affordances of that is to say there's a few courses that are particularly amenable to this. And maybe we should kind of more broadly rethink those particular courses. StatMech, Optics, Advanced Lab. And these are things that were highlighted in the decadal study, that this is a particularly ripe area to incorporate biological physics into the undergraduate curriculum. Thirdly, is to say, well, maybe we need to develop a special program for students who want to focus on biological physics, and that those students, will take extra courses or have also options of courses that bring in the biophysics. And then the fourth option is to much more radically rethink the undergraduate program. And we're not going to try to do that today. We're going to focus on the first three, which are more straightforward and that we have some clear examples to offer. This is not to dismiss the possibility of radically rethinking the undergraduate curriculum. And I know from just looking at the names of folks who are on this call that several of you would like to do this kind of thing. And maybe we can have a separate one where we just kind of brainstorm about that. But today the focus is on those first three somewhat more incremental lanes and hearing from people who have some experience with them. So we'll hear from each of our three panelists for about 7 minutes each, and then we'll go into breakout rooms divided by those panelists corresponding to those lanes. So Janne, can you take us first on how ways you've incorporated living physics into the existing curriculum?
Yes. Hi, everyone. Thank you for joining. I guess before I start, my real hope is that we can just blow up the whole curriculum, but maybe, as Catherine said, that's for a different conversation. So I was going to just kind of briefly tell you a little bit about the efforts we've made here at Brandeis. So I'm a professor of physics at Brandeis University. And I guess for about 20 years now, we've been trying to kind of think about ways of incorporating biological content into physics courses. And where I think we've made the most progress is in thinking about how to do that at the first year level, so at the point where students are entering the university and taking their introductory physics class, which is usually a 2-semester one. And so what I want to tell you about, what I want to just give you a brief description of is a sort of add-on to the introductory physics class, which I've taught for a number of years, where the goal is to, as these sort of little sort of quotes are meant to suggest, is to both put some numbers into biology, but also, as I said, introduce biology into physics. And kind of the scheme is to sort of follow the usual progression of ideas in introductory physics, from mechanics and thermodynamics to modern physics, and try to, at every stage of the game, bring up topics in modern, mostly cellular and molecular biology, and that is just a reflection of my own interests and the things I know a little bit about. So I just thought in the few minutes I have, I'll just try to give you a sort of a sense of this through a vignette. So the course tends to, it's a 1-semester course. It has units which change from year to year. I picked one, I think, from an earlier incarnation of the course, but the goal is for every unit to have a particular sort of example in biology, an interesting problem, hopefully something that's very current, and then also to use it to illustrate a physics concept. So I thought I'd just kind of give you a very brief sort of show and tell of how we use sort of the bacteriophage life cycle to talk about force and energy. So this unit would start with sort of a general discussion of what are viruses, how big they are, how much how much DNA they carry inside them. And here's a sort of a EM picture of a bacteriophage, a virus that infects bacteria. And you can kind of see these black lines are actually the DNA that's very tightly packed inside the virus. And then there's some, this is a particularly nice example because there's this beautiful animation that came out of UC Santa Barbara, where they kind of took a lot of the experimental work they did, which was started by Carlos Bustamante, of looking at the forces involved in packaging of DNA inside the virus, the purple thing being the DNA. And by using sort of an optical trap apparatus in this experiment, they're able to see how the force that's resisting the packaging of DNA, the buildup of the internal force varies with the length of the DNA that's being injected. So here's the graph again. And so this immediately kind of gets us talking about the area under the curve being the work done by the motor. And just by looking at this and knowing about the energy of a spring, the students come up with an estimate of about 75 piconewton microns. And then there's sort of a two-class long discussion of should we be surprised by the work being 75 piconewton microns? What does even piconewton microns mean? And so forth. So it gets us into all sorts of interesting kind of physics and chemistry as well. So that, and then you know, we go through a bunch of other similar vignettes to discuss other problems in both biology and physics. And like I said, I don't have time, but whoever's interested, certainly I'd love to chat about it more. And I'm happy to share all this material if anyone wants to incorporate it in their own teaching. And then I would just also point out that so in addition to talking about how physics ideas fit into biology and how we can illuminate biology with the physics, we spent a lot of time in this course trying to teach students how to do simple estimates and the power of simple estimates. And so, for example, we'll start with a picture of a bunch of ribosomes in E. coli, which sort of just like counting jelly beans in a jar quickly leads to an estimate of about a few tens of thousands of ribosomes. And then we can see how this is really interesting, because if we make other simple back of the envelope estimates, and in particular how much amino acid there is inside the E. coli bacterium, then we can, by knowing that the cell divides in 30 minutes, quickly come up with an estimate of how fast each ribosome is producing proteins, and that's about 25 amino acids per second, which then can be sort of discussed in the context of more modern experiments, again using single molecule technology. So that's another sort of a big theme in the course, is getting students comfortable with making these kinds of order of magnitude estimates. And I would just like to kind of end by saying, you know, a great resource that we use, and sort of there isn't really a textbook for the course, but a resource I use a lot is the book by Ron Meal and Rob Phillips by Cell Biology Numbers. And the way I use that is there are vignettes in this book, and I'm not going to, you can look at it yourself, but students actually each pick one of these vignettes and they present it in the classroom. And these vignettes have also these two key ideas in them, which is one is making estimates and the other is using simple physics concepts to talk about biology. So I think my time is up. I haven't sort of paid attention to the clock, but I will stop there.
Yeah, your sense of time is perfect. I had 45 seconds left on my timer there. So do you want to add 30 seconds worth of something?
Yes, I think we should blow up the standard physics curriculum. And anyone who's interested in having those discussions, I'm all for it. So I think, I should say, you know, I grew up in a communist country, but I'm mostly an anarchist. So I would like to see this happen in my time.
Nancy, I think we'll need to program a discussion of blowing up the physics curriculum for the spring if DBio wants to take that on. So, well, thank you so much, Janne. That was so great to hear about these things you're doing. And I apologize. I'm figuring everybody wants to hear what our panelists have to share rather than me introducing them. So I'm making that assumption. So next up, we have Ashley Carter from Amherst College, who's going to be talking about revision specifically to those low-hanging fruit target courses.
Hello, everyone. My name is Ashley Carter. I'm from Amherst College. I do have some slides as well, so I'll share my screen. Oh, I don't think I can share my screen. Catherine, can you make me a co-host, so I can share my screen? If that's possible. Oh, wait. No, wait, I can. Okay. Can you see my screen now? Okay, good. Slideshow. Okay, so I'm tasked with lane 2. This is the easy lane. This is like, you know, if you want to just make some quick changes to your curriculum, this is the lane to go. to do. And I'm specifically going to talk about updating statistical mechanics and advanced lab. I won't touch on optics, but that is the other course that was identified. The impetus to change our curriculum, I'm at Amherst College. It's a small liberal arts college, 1,800 students. We have about 15 students per year in physics and astronomy. But we have this new biochemistry and biophysics major. And by new, I mean it started in 2012. But now it has grown to about 30 students per year. So it completely dwarfs our physics and astronomy population. If you would like to start a new major in biophysics, I'm just going to put the biophysics has a website up there, and I'll put it in the chat afterwards. The other impetus for updating this physics curriculum was that we really moved away from being like grad school prep. Like our goals are really for grad school prep before I got there. And now our goal is really to create like an interdisciplinary physics major. And like, because really we're giving a BA, we're giving a bachelor's in art and physics. And so really just thinking about that more broadly, having more electives, being much more inclusive about the type of physics that we do. So both of those things have led to a big increase in the numbers of students that have taken our classes, but also in an increase in their what they want to do. And they're not going to physics grad school. So there's two updates that we've sort of made to deal with the 30 per year biophysics, biochem majors, and to capture these students' interests. The first one I'll talk about is updating the advanced lab. Our advanced lab, the students rotate through a series of experiments. So just adding another experiment on the biophysics is a really easy thing to do. Except you have to train everybody in your department on how to use that experiment. But one that's really nice, and this is the best experiment to put in, is the Brownian motion experiment. This one is really great for a couple of reasons. You can do a random walk. Physicists love random walks, so they're very exciting for like a lot of different reasons. There's no biological sample, so you don't have to worry about like knowing how to pipette or anything. You can use almost any microscope. So like some microscope that you have lying around or the biology department has lying around, you can use for this system. And you can also do particle tracking with programs that are free and that actually get used in laboratories and research science. So this is a really good one. If you, my student and I wrote a paper on using this one. Oops, sorry. It's an AGP in 2012. So this is the one that we actually use in Amherst College. The other experiment, okay, so yeah, so let me just say that basically what you do is you have a microscope, you've got this sample here with beads. The beads you can see here, they look black. They move around in the water. You track them, and then you can tell things about, like, you can either measure the viscosity of the water, you can measure the Boltzmann constant, you can see their random walk. So you can see lots of really fun parameters. The other experiment that we chose, but may not be the best experiment for everybody, is to do AFM images of DNA. For this one, you need an AFM. We bought like a teaching AFM for about $15K to run this experiment, and that has worked really well. But you might have an AFM on campus, and that's fine. So this one is fun because you get to use an AFM, so students can use an AFM. You buy the biological sample, so still you don't have to prepare a biological sample. Here, you're buying DNA that's on mica, and you can measure all of the polymer physics. So you can measure like persistence lengths, and if you can measure a lot of really fun polymer problems. There's a paper that my student and I wrote on this one as well, and this is the lab that we use in our advanced lab. So this one's in AJP 2016, if you want to take a look at that one. The other really easy thing to do, I say easy, but relatively so, is to update statistical mechanics. So we have these 30 biophysics, biochem majors that are coming through. They're all taking statistical mechanics. So they're taking the 2 intros and then the statistical mechanics. And so we wanted to make this course accessible for them. And I say we wanted to make it accessible for them. The best person every year in this course is a biophysicist because they have had so much thermodynamics. So like, you know, the best student is going to be them. So you don't have to do too much for them, really. The thing that they don't have strength with, so they have lots of thermo knowledge. The physicists usually do not have any thermo knowledge. Like for whatever reason, we don't do any intro thermo. And so they're just like thrown into this class. They have no idea what's going on, but they know they have a lot better math background. The biophysicists, they know tons of stuff about entropy and energy, but perhaps don't have like the probability or the differential equations, like to do a lot of the pushing of the differential equations. So they have different strengths. So to sort of like characterize that, what we did was we put in 4 weeks of introductory thermo. So like literally right out of Young and Friedman, or there's an OpenStax book, 4 weeks of introductory thermo so that everyone's on the same page. The biophysicists who've never been in a physics class, they're feeling very comfortable. And then the physicists are also feeling very comfortable. So after those 4 weeks, everyone's feeling really good, right? The homeworks were good, everything was good. And then we switched to the statistical mechanics book. And so we used to use Schroeder. I think Schroeder is an excellent book, but we actually switched to Dilla and Bromberg, which is the book they use in physical chemistry. And the class is taught at the same time as physical chemistry. So the students have a choice between them. And so they feel like, oh, this is like a book for me, for whatever reason. The other thing, the reason to switch to D&B is because it does a lot of the heavy lifting. There's a lot of biophysical examples in that book. So even if you do decide, like, I still want to use Schroeder, which I actually might do this next year, if you look at Dilla and Bromberg, there's a lot of biophysical examples. So it's not about training them, it's about training you on like, what are the biophysical examples that I'm going to put in the class. I see you, Catherine. Okay, and then the other thing is that we added 3 weeks of a group project so that way the students can pick these biophysics projects. This was actually really good for the astro students too, because then they picked a lot of the astro projects. So it was actually really useful for everybody. So the astro students got to do astro, the biophysicists got to do biophysics, and everybody seemed to be happy. So those are my top 3 things to do. If you just want to see some of the biophysical examples, like, you know, like which ensembles might you use for like molecules in a liquid and a test tube? Like if you have a single protein in a liquid that folds, like what ensemble might you use? You know, we had a challenge problem where we were talking about cells growing in liquids, exchanging particles through their membranes. That's like a fun one. The other problem that we did was when thinking about 2-state systems, about folded and unfolded molecules, about substrates binding. There was also a really fun one about channels. So there's a lot of really good biophysics, and just like incorporating those examples is really good. So those are the easy lane 2.
Thank you so much, Ashley. And now for our final panelist, we're going to switch to Patricia Soto Becerra. I'm probably not pronouncing your last name right. I'm so sorry. And let's see, Ashley, can you stop sharing so that if Patricia wants to share, she can? Awesome. And Patricia is going to share about the biophysics program that she directs. Is that right?
No, I don't direct that program. No, I'm not the director, but I'm going to talk about that. Okay, so everybody sees my slide, right? Okay, good, thank you. So yeah, Catherine, actually your pronunciation was quite good. I appreciate that. So what I'm gonna do in the next 4 slides is to tell you the story of how in my department we have a program targeted to a group of sciences that are identified as either biological physics, biophysics, medical physics. So we have all these programs in us. Some advantages that we have in my department is that 3 out of the 9 faculty are either medical physicists or biophysicists. So we have already that background, and we all have a shared understanding of the meaning of education at our institution. So what is our institution? And the reason why I want to talk about this is that when we develop programs, the context matters a lot. So we are a private, co-ed, comprehensive Jesuit institution located in Nebraska. My physics department offers undergraduate degrees, and also we have a small master's program. I made a mistake. It's a small that is growing master's program. So that's our terminal degree. Regionally, our institution is known for health sciences. So that's the big thing that brings students to our institution. And therefore, one of the reasons why this physics department was created was to support the training of medical pre-meds and then medical students. However, there is a tension at our institution, which is the balance, or actually the unbalance between being a teaching center institution and being a research intensive institution. We all think, and when I say we, I mean all my physics colleagues, we all think that if we develop our programs in biological physics or medical physics, we are going to increase recruitment and retention of students. We also believe that that will build or complement the generalists program that we have. And we see a little bit of a barrier in that our students in college are exposed to physics only after they have done Gen Bio and Gen Chem. So that's a little bit of a barrier that we think it is a barrier, but sometimes I think it is not. So based on this context, we develop, and when I say we, I truly mean all the faculty, we develop an undergraduate major in biomedical physics, and I'm going to talk about that on the next slide. We have a master's in medical physics that has been growing in the last years. And we also have a master's in physics. And for the students that have the master's in physics, some of them do a thesis in biological physics. So to give you a sense of how big or small our department is, I want you to know that in average, we graduate between 10 and 15 undergraduates each year. And in our master's program, when we had only the master's in physics, we used to graduate about 3 students per year. But now we are graduating twice that number because the medical physics master's is becoming very popular and has doubled the number of graduates that we have. Let's see, how do I go to the next slide? Like this. Okay, so this is how the biomedical program looks like at our institution. And in here, I have to give all the credit to my colleague, Mike Nichols. He did all the bureaucracy and administration and persuasion to make this program happen. So basically, we have our Physics for Life Sciences general courses, and we expect all the students to take modern physics and research methods, which is a course that for us bridges from the intro lab courses to the upper level courses. And then from there, students have 2 options. They can either take a course in physics in medicine that focuses on radiation and imaging. And the other course is Introduction to Biological Physics that we usually teach with Phil Nelson's textbook, although we have tried also the Rob Phillips and others textbook. And then after the students take either of these courses, then we have tracks depending on the academic goals of the students. So if we have students that are more into engineering, like we have a collection of courses for them. If we have medical physics students that most likely are gonna follow masters at our institution, we have another collection of suggested courses. Or if we have more biological physics students, we have other courses that we suggest them to do. Something that we do at our institution, because we are a heavily pre-med and pre-health institution, is that all the electives and all other options in our majors overlap with all pre-med requirements, with the goal of making this transition easier for the students. So how can we make this happen in a physics department? So the way to do it is by building sustainability with all your colleagues that are not biological physicists. That's how we can make it happen. So the first set of changes that we did happened in the introductory lab courses. The first design was done by my colleague, who is a condensed matter physicist. So he built a collection of labs in radioactivity, fluids, and thermodynamics. They do Brownian motion. Ashley, I'm pretty sure the Brownian motion that we do in our lab is way easier than yours. But hey, still it has a 1D random walk. Okay, I have 1 minute left. And then the course has been adopted by other colleagues who are non-biological physicists. Another example is bridging nuclear physicists into our program. So my colleague teaches modern physics and nuclear physics for this group of students. And then, yes, of course, we have biological physics and medicine taught by ourselves, the biological physics people. Something that I have found interesting, and I want to mention very briefly, is that when we teach biological physics courses, because we get students from different tracks, an issue that I have is how to assess the learning of the students. So for that, and perhaps because that is my actual field of research, right? I like to implement course undergraduate research experiences or other types of artifacts that assess the learning of the students. So from this slide, I want to tell people we just have to bring in the non-biological physicists, build a course that they can literally copy and paste and just do it, and then it should work. So I should finish. I know I'm running out of time, so I'm going to finish here by showing my wish list. My wish list in terms of teaching biological physics. There is no time for me to go through everything, but I have to highlight two things, Catherine. Is that okay with you? I have to highlight that I want to know what thinking as a biological physicist means, because from that thinking, I can design my courses. And I, of course, want to invite everybody to read everything that I wrote, or we can discuss it at the breakout room. And I really want the audience to read and submit to the Biophysicist Journal. I'm sorry, this is pure advertisement, but here is the thing. What is the advantage of this journal? In this journal, we are interested in scholarship of teaching and learning. And the readership already comes from areas other than physics alone. So that barrier has been crossed, and we have readership from physics, chemistry, engineering, medical physics. So this is a venue that I will invite you to read and submit to. I'm going to stop here, Catherine.
Patricia, thank you so much. And of course, every one of our panelists, can you stop sharing, Patricia? Sorry.
Give me 1 second.
Sure.
I'm going to stop shade.
Every one of our panelists, I'm sure, could have shared for much longer. And I'm sure many of you out there have intense questions that you want to either pepper them with or pepper each other with. And this is by design. So now we're going to go into breakout rooms. And the breakout rooms are named by, roughly speaking, the combination of the lane that each panelist addressed and the name of the panelist. And those panelists will be in those 3 breakout rooms. It should be set up so that you get to pick which breakout room you want to go to. And here's just the general guidance for what should happen in these breakout rooms. Hopefully, people will divide themselves roughly evenly so that each group is small enough that people can, at least many members can participate. When you begin to either ask a question or share something from your own experience, please introduce yourself to start with, and then either ask a question or share something from your experience that is relevant to this topic. And then we will go until the hour is up. We will not return here. So your panelists are moderating these discussions and they are free to lead these wherever they go. So this is just a time for everybody to gather. So because we're not going to come back together, I do want to just take 1 minute to thank all of our panelists for taking the time to put this together and share. So thank you all so much. And thank you to Nancy and DBio for inviting us to do this. And so now I will open the breakout rooms, and you all should be able to pick the room you want. Except for the panelists who are pre-assigned.
And if anyone has issues putting themselves into a breakout room, just let Catherine or me know and we can manually assign you to a room.
Well, it looks like almost everyone has found their way into a breakout room or has left.
Yeah, not exactly an even distribution.
Well,
But
Nancy, feel free to head to a breakout room and I'll stay here for a couple of minutes. Let's see, William, you have your hand up.
Yes, I am one who cannot figure out how to get into a breakout room.
Okay, so I think that what you do is you, I think you, in the menu at the bottom under more, there should be a breakout rooms option.
I see that now.
And now you should be able to pick one to join.
Oh,
So-
I see. Yes. Well, thank you very much.
Oh, sure. Good luck.
Thank you.
Cool.
Oh,
Okay.
Nancy, you decide where you want to go.
Yeah, I
you-
like the one I was most interested in as the most popular one, so I'm thinking we'll go to a different one. Maybe I'm gonna, do you want to also just stop the recording at this point?
Oh, good.
The
good.
file is manageable
Yeah.
for, yeah.
Yeah.